All right, everybody, here we go. Week 11, day 2. Solving equations with Algeblocks. Of course, we all know how to solve an equation. Let me give you an example. How about something like 3x plus 4 equals, let's make it something that's relatively nice. 21. Nope, 22. Let's do 22. There we go. Alright, sorry, I should have made up an example at first. I just want to show you how the last mat works. So we're down to our last mat. Some of you actually have asked me, what about this third mat? I don't know what it is. And the third mat is called the sentences mat. Okay, Algeblocks sentences mat. I'll try to put that glare right in the middle. Okay, so you'll notice that it's got an equal sign in the middle. You've got basically what amounts to the basic mat on the left and on the right. It's got a positive and a negative. And what is this? That's a balance, right? Okay. And we all know, we've heard it been said before. If you haven't, now's the time you're going to hear it, that anytime you work with an equation, you have to do the same thing to both sides. And the reason for that is because you need to keep your equations balanced. Okay? If I take off 5 off to the left and I don't take the same 5 off the right, then basically I'm taking 5 off of this one. This one's going to be heavier, and the teeter-totter goes like this, right? So I'm literally dealing with what's going on. If I do something to one side or the other, I want to keep it balanced. So that's the reason, by the way, we made you a couple of weeks ago do balanced logic and the seesaw stuff. So you would have that idea in my brain, in your brain, okay, that everything that's happening here, I've got positives and negatives on both sides, an equal sign in the middle. That tells me the sentence part is that it's an equation. So it'll say something like, well, let's do the one we have. 3x plus 4 equals 22. And in our brains, we can say that equals is about the same as saying is. 3x plus 4 is 22, right? And because they are equivalent, I need to treat them equivalently, okay? So I've got 3x, I'll stick them on this side, plus 4. And I'm thinking to myself, why did I pick such a huge number, dang it? Okay, 3x plus 4 equals 22. Okay, 3, 6, 9, hopefully I count better than I did last time, 10, okay, 3, 6, 9, 10, and I need 2 more. So just going to check myself because a second ago I clearly counted incorrectly. So I'm grouping them in 5s just so I can see where I am. Alright, there's 22. We're good. Alright, so on the left-hand side, I've got the 3x plus the 4, and on the right-hand side, I've got the 22. So we're going to use all of the stuff we've done with Algeblocks so far and try to make it all work out, okay? And we're going to do it in the same way that we would solve an equation. So if I wanted to solve an equation, what I'm seeing here is I've got 3 x's, so that's a multiplication process, right? And I've got a plus 4. And in my brain, going off like ping pong is just ponging around inside of my brain. I need to undo that stuff, okay? So I need to undo the plus 4. And how am I going to do that? What's the opposite, or what's the undo of add? I'm adding 4, okay? Well, we know if we were doing this right here, we would what? Subtract 4. Okay, those guys would go away. And I'd have a 3x equals 22 minus 4 is 18. So that's one step in the process for solving this equation. So I'm thinking to myself, how in the world am I going to do that? Well, I need to minus 4 on both sides, subtract 4. And we know that subtraction is the same as if something's on my mat, I need to take it away, right? So I'm going to take 4 off of the left-hand side of the mat. Okay. But I can't just do it there because what's literally happened is I picked off stuff off of this. This side got lighter, so the heavy guy, this is now going to be the heavy guy, and it's tilting, right? Okay, so don't do that. You got to take off both sides. So I took 4 off the left-hand side, so I'm going to take 4 off the right-hand side. All right. Okay, now if I did my arithmetic in my head correctly, I've got 3x equals 18. So 5, 10, 15, 18. Okay, hopefully we can all see that. And I'm thinking, what in the world can I do? Can I somehow group those together? And the answer is absolutely. Okay, so whenever I think about it, I'm looking, I actually say 5, 5, 5. And if I just put one of these on the end of each of those, make sure they're all positive because they were positive to begin with. Okay, so if I just put one on the end of those, I can see 3 groups of 6, right? And if I separate these out, I can see 3 groups of x's, 3 groups of 1x. Okay, so what I'd like to do is use that division process that we had before whenever we wanted to split a group into 3 groups, because I see there's 3 x's. And I basically want to assign, well, how much is each x worth, right? Okay, so I'm going to, let me line them up side to side so we can see it better. You don't have to line it up side to side. You can just have them grouped in 3 groups and show me, okay, they're equal groups. They're definitely equal groups, right? 6 in each, 6, 6, 6. And 1x, 1x, 1x. So I've gotten them split up or divided into 3 groups. So the idea here, again, over here I've got 3 times x. That's multiplication. How do we undo multiplication? By dividing. So I'm splitting up the stuff here on each side of the equation equally into 3 groups. And so I'm saying, okay, I'm going to divide by 3. And what do I get? X equals 6, right? Yep, we got it. Okay, so here, what do I have? Each of my x's is lined up with a 6. Okay, I don't need all 3 groups, right? I just need one of those groups. So I'm going to get rid of these guys. I'm just looking at what is one group equal to. 1x is equal to 6. So this would be those equivalencies that we saw whenever we were doing the balance logic, right? We had a lot of that going on. And we can see 1x, if 3x's equals 18, split them into 3 groups, 1x equals 6. That's not bad, right? So we've done like undoing addition, and we did undoing multiplication. In general, that's the way it's going to work, is we're going to be doing division and doing adding and subtracting. Those are the normal types of processes that we use. We also know, for instance, if I had a fraction like x over 4, I could multiply by 4 to get that guy by itself, but that doesn't happen very often. And what about doing that with Algeblocks? This is a limitation. Yeah, it's hard to show x divide by 4 on these Algeblocks, right? Because I would need a fourth of each x, and that's just not going to happen for me. So we have to kind of think about it as we develop equations to work with our students. Okay, what operations can I show very easily? What operations can't I show very easily? So I can show division real easily. I can show adding and subtracting very easily. I can show the difference between a positive and a negative pretty easily. I just can't show the fraction stuff. So I can't show in an equation how I would multiply, basically. It's hard to see. Okay, so here's my next problem. I'm going to do 2x plus 5 equals negative 7. I'm going to work out the math real quickly just so we all know. First step here would be get rid of this 5. So I'm going to subtract 5 both sides. When I do that, I'm going to end up with extra negatives, basically, right? So we're going to have fun showing how that works. That gives me 2x equals, that goes away, and this is going to be negative 12, right? Okay. So remember, the process that we just did here was take away a positive 5. The minus here, the subtraction sign means take away, and we're taking away a positive 5. So we're going to play with that in a minute. We're going to see how that works. Okay, but now I've got 2x equals negative 12, and mathematically we're just going to, divide by 2. Those are going to go away, and I'll have what? X equals negative 6, right? So when we finish, we'll know we're in the right spot. So I started to say earlier, sometimes as the teacher, it's nice to kind of have a feeling for where am I headed so that we can see, okay, we're in the right place, we're not in the right place. Then we can do some other stuff. Okay, so here we go. 2x plus 5 equals negative 7. I'm going to model that first. Hopefully, you guys have a printout of this larger mat. You're going to want that to be able to show me stuff in your video in a couple of weeks. 2x plus 5 equals negative 7. So hopefully you've got that printed out. If not, try to get it printed out. It's going to be pretty difficult to show me stuff using the mini mats that we're doing for our homework, right? So try to do that. Now the problem is I need 2x plus 5 equals negative 7. So over here I need negative 7. And that means putting all these 7 guys that I've got in my hands down here on the bottom. Everybody okay with that? Okay, so I need a negative 7. Okay, and this is where I said we're going to have a tiny bit of fun with this because hopefully you see the problem. You're like looking at it going, what in the world? So I'm looking at it saying, oh, I need to take away a positive 5. Well, I'm going to take those away on the left-hand side, but I also need to come over here and scoop up and take off 5. I don't have them, right? I want to take away 5. That's the operation. The operation subtract, one more time, means take off the mat. Okay, I want to scoop them up and take them out. I don't have anything there to take out, so I can do it on the left-hand side, but I can't do this on the right-hand side. And I need to make sure everything works out evenly so that I'm not throwing my balance off, right? So what do y'all think? How am I going to get 5 there so that I can scoop them off? 0 pairs, right? It's got to be. Okay, so I'm going to put 5 up here so that I can perform that operation here in a second. But the problem is, I just did this, right? I put 5 there on the top, so it's throwing me off. So I want to make sure that they're balanced evenly. If I put positive 5 there, I need to put negative 5 down here on the same side. So it's like plus 5, negative 5, that's a 0. I changed the way it looks, but I did not change the value. Okay, make sure you're doing that. So I'm adding the positive and the negative on the same side of the equation. And I can show you what that looks like in a second if we want to see that 0 pair coming in. Okay, so that's what happened. Now I can perform the operation subtract 5 from both sides, right? So I can scoop 5 off of this side, I can scoop 5 off of this side. Those are all my positive 5s, they're all going away. And now I'm thinking to myself, that's kind of unusual looking. I'm going to point these at each other just so that we can see. This is 2 x's. I know I only want to know what one group is worth, right? So say I don't know that 12 divided by 2 is negative 6. What I can do is just literally start, as a kid in particular, grouping them into 2 groups, right? So I can start splitting them up and saying, hey, I didn't even count, but how can I split those up? And I'm trying to kind of line this up so that you can see that X goes with those guys and that X goes with those guys. I do have a glare on the mat. I should have printed a paper one of these so we could see them. Okay, but I do have 2 groups here in the left-hand side. I do have 2 groups here on the right-hand side. I'm making them point across the equal sign because I see one is in the positive side and one is in the negative side. I want to make sure we see those are my 2 groups. I only need one of them to talk about, so I'm going to get rid of that. That's the division process. I split them up, and I'm just going to talk with 1x is equal to 1, 2, 3, 4, 5, 6, negative 6. Okay. Hey, it's the right answer. We know. Okay, so that's kind of how those work. All right, so let me just real quickly show you what the process was here. I wanted to subtract off 5, right? And we know that basically we're going to add the same thing. I'm sorry, add these together because they're the same negative sign, and just take the sign of the negative number, right? But really what's happening is before I can do that, I don't have a 5. That's why I said this is going to be interesting. I don't have a 5 to take away. What I would have done is done plus 5 minus 5, right? Or plus 5 plus a negative 5, okay, is what I really do. And then I could minus those two 5s out. And I'd be left over with this negative 5 that it's just sitting there, right? And then I'd combine my like terms, negative 7 plus a negative 5. That's where the negative 12 comes from. Okay. Okay, I think just one more of these because I feel like between the balance logic we've done and all the work we've done with the Algeblocks, I feel like we're probably getting the good idea. I just want to make sure we've got one more because what would it look like if I had a negative sitting in the problem? So here we go. 2x minus 3 equals 9. And again, we'll do the math and then we'll see how the Algeblocks tie together. So 2x minus 3 equals 9. I wanted to get rid of this minus 3, so I'm going to what? Add 3 to both sides. Those will go away. I have a 2x is equal to, these were nicely came together, 12. Okay, and then I've got the subtract, or the division part, right? All right. Now, I would like to note that the answer is not always going to be a 6 or a negative 6. Okay. That just happens to be happening right now because I'm trying to pick relatively small numbers. So, of course, we know we can solve these equations and we'll get whatever, right? So, it doesn't have to be a 6 or a negative 6. All right. So, now let me see what that looks like. 2x minus 3. I want to model that on the left-hand side over here. The 2x is good, but I might need to come up with the fact that the minus 3, we talked about it a week or so ago, maybe longer, is equivalent to a negative 3. So minus 3 is the same as plus a negative 3, right? And we talked about that and when those are equivalent and how we can show it. I don't really want to go back through all that again, but we know that those are equivalent, and I need equals 9, right? Okay, equals 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we said that we're going to add 3 to both sides, and this is what I think is interesting about this one. Whenever it was a positive 5 up there, I just said I'm going to subtract 3, right? The problem is if I want to do that here, and you can do it that way, if I want to subtract 3, I'd have to take these negative 3 off the board, right? I'd have to subtract negative 3, which is equivalent to adding 3, so that would be okay. And the problem is what? Over here I don't have any negative 3s, okay? So I can do it with 0 pairs if I want to. I can put in a negative 3 and a positive 3. That way I'm zeroing out, I'm not changing my value. And then I could scoop off the negative 3s and leave those positive 3s would stick behind, right? And it would actually kind of mirror the process we just did a second ago. So we can do that if we want to, and you're perfectly welcome to do that. It's perfectly mathematically correct and all that. But I want to actually model what we said we were doing. We said we were adding 3 to this side, right? So we didn't say subtract a negative 3. If we'd said subtract a negative 3, that would have been a take away model. But this is add 3. So I'm going to add 3 onto the board right there, positive 3, right? And whatever I do to the left-hand side, I do the right. So I'm going to add 3 to the board there. So that's this process right here, add 3. Okay, and what I see is an interesting thing happens. I get to avoid doing the 0 pairs at the beginning, right? Add the negative 3, add the positive 3, then scoop off the negative 3s. Okay, so I get to avoid that, but I have created a 0 pair issue on the left-hand side now. So I could have put on the negative or the 0 pairs on the right, but I didn't. So now I have a 0 pair thing going on the left. So ignore the right-hand side for a second. I don't care about that. What I care about is what can I do when I have 3 positives and 3 negatives there. And of course we know, right? We can pair them up. That's a 0, that's a 0, that's a 0. And when we get that, we know plus 3 minus 3, or plus 3 plus a negative 3, however you want to think about that, that's a 0 pair, so I can take it off the board, right? Okay, so as soon as I have a 0 pair, I can take it off the board without changing any values of anything I'm working with. So that's awesome. Okay, and then again, I can do this dividing by 2 thing the same way that I did it earlier. Just split these into 2 groups. We already know the answer. Okay, I've got this x is equal to these 6, and this x is equal to those 6. So I can just look at one pair, or I'm sorry, one set. So one set, 1x is equal to 6. There we go. Okay. Just for funsies, so we all know it doesn't always equal to 6 or a negative 6. Let me just do 5x equals 10, and we'll model that real quickly so that we see it. I would divide by 5, right, both sides, and I would end up with x equals 2. That's the math that's going on in the background. So let's just see how that looks. It's a pretty easy setup. 5x equals 10. Just so we all know. Okay. And then I would split these into 5 groups, right? Because there's 5 x's. So I want 5 groups. And we know that if I take 10 units and divide them into 5 groups, there will be what? 2 in each group, right? So I can see those lining up. All right. So there's 1x equals 2, 1 equals x equals 2, 1x equals 2, 1x equals 2. I can get rid of all of those. I just need one set. One set, 1x equals 2. Okay. So the answer is not always 6 or negative 6. We knew that, but we just want to see it demonstrated sometimes in our blocks. Okay. So that's really it for the Algeblocks. You can see we've spent a couple of weeks going through a lot of different things. The niceness of them is that we can use it for all kinds of stuff. So we did integer operations. We did add, subtract, multiply, and divide with just whole numbers and their negatives. Again, no fractions. We couldn't do 3/4 plus 1/4, right? We can't do that. Just because we can't do fractions using, we've got a whole entire x, right? We can't split it up very easily. So it's hard to do that. So that is a limitation of any of these blocks. But it's true of pretty much any manipulative. It's very difficult to do fractions unless I come up with a manipulative that was designed for fractions, like Cuisenaire rods or fraction circles or something like that. But I can do integer operations. I can do operations with with variables and expressions is what I tried to say. Okay. So for instance, if you had a binomial 2x plus 3 and you wanted to add that to 5x minus 4, okay, we could do that using our blocks, right? Okay. And then we know that we can multiply and divide variable expressions, which is part of the operations with them. But these two are particular, right? We did a lot of work with those, so I want to make sure we know those are two of the operations that you're going to see coming up on the test, where you're going to have to multiply and divide with variable expressions. Okay, we can factor, and in particular we're going to talk about factoring trinomials. Okay, you can factor other stuff too, binomials, 4 terms, whatever, but we saw mostly trinomials that we were working with to make our rectangles. And I'd like for you to be able to tell me how that can tie to the AC method, because I spent time on it this week. Okay, and then the last thing that we have seen that we can do with these algebra tiles or Algeblocks is solve equations. And in particular, we can solve equations by adding, subtracting, and dividing. I could multiply with them. I would just have to take whatever sets I had there and duplicate it over and over again. But again, that ends up looking a little weird, so we're not going to do those. Okay. And as always, there comes a spot where there's a limitation to the manipulative. I just can't take it any farther, right? I can't do the fractions. I can't, do the multiplications. If I had something like, let's keep it easy, 1/4 x plus 3 equals, let's just do 10 or something like that. Okay, those are going to be weird things, right? Because when I subtract the 3, I'm going to get a 7 over here whenever I do that, and then I'm going to need to multiply that by 4, so I'm doing 7 times 4 is 28. So it's a very solvable equation. It's not a problem from that point of view, but using the manipulative to do it becomes cumbersome. And what we don't want is we don't want the manipulatives to be so cumbersome for the children, for the kids in your classes, that they're stuck on, I just can't move these blocks. Okay, that's not the point. The point is for them to see something nice and pretty and concrete that will tie with all of this weird abstract math that we're making them do. Once they know, though, okay, I can solve equations with this, and they can see the doing and the undoing and all those algebraic habits of mind that we've been doing before in the class, when they can see that coming out, then they go, oh, okay, I get it. So if we're dividing, which is what this is, then what's the undo for that? Multiply, right? So then they can work in the abstract and they can take this and just run with it. Okay, because again, at some point, and bless you middle school teachers' hearts, okay, if you're a middle school teacher, we're taking them from very concrete stuff in the elementary schools to very abstract stuff in the high schools. I've said this before, and it's your job to bridge that gap. And it's really tough, and that's why I want you to have this particular manipulative in your tool bag so that you can work with it, whether it's the algebra tiles or the Algeblocks. Okay, I think I mentioned how expensive the algebra tile or the Algeblocks are. So if you go to a school district that doesn't have those, it's okay. Just get algebra tiles. You can get a whole set of those, a classroom set, for not too much money, especially compared to the Algeblocks. Okay, what else was I gonna say? If you're, that's for middle school teachers. If you're a high school teacher, of course you're probably not doing integer operations, but you might be. You might have some students that are your special ed kids or, different inclusion type stuff that they need some lower level operation stuff. They still don't get why a negative times a negative is a positive, or why when I add a negative and a positive I subtract the values and take the sign of the bigger number. So you could work some of that stuff out and fill in some gaps for some of your students with that at the high school level. But really where we're going to end up using it is in the operations for the variable expressions, the factoring. This factoring one is the one that I've seen the most on the STAR exam that the kids will take. Okay, so you might see a question about factoring trinomials in your Texas exam to become a teacher, because they want to make sure you've at least seen the manipulative and know how to use it with your students. And then the high school algebra EOC, that test, algebra 1, they're going to see, okay, which of these is the appropriate rectangle for factoring this trinomial kind of thing. Okay, so you need to show them that, but not just because it's on the test, because it's actually a really cool manipulative and you can do a lot with it, right? Okay, so that's it for Algeblocks. This second video is pretty short. I hope you understand how to use them to solve equations. If not, shoot me an email or drop by my office and see me. If you have any questions, let me know. All right, thanks. That's it for week 11. Woohoo! No more week 11. See you soon.